Hey everyone, in this video I'll be giving a review for test 2, which is on chapters 4, 5, and 6. Okay, so chapter 4, which is on probability. Let's talk about what are some of the really important things we need to know. Well, remember, what is probability? Probability is the number of favorable ways of doing something over the total number of ways of doing something. And so it's always going to be a fraction between and including, 0 and 1. Probability is going to be between and including 0 to 1. The probability of 1 means it's definitely going to happen. It happens 100% of the time. Probability of 0 means it will never happen. And of course, anything in between, written as a decimal, will tell you, or a percentage rather, will tell you the percentage of how often that thing happens. Right? Probability gives a decimal. If you want to give it as a percentage, then you multiply by 100. Just move the decimal 2 spots to the right. Okay, and so remember, in a probability experiment, aka just a probability question, remember the sample space is the set of all possible outcomes. So if you're rolling a 6-sided die, the sample space would be 1, 2, 3, 4, 5, 6. If you're picking a card from a deck of cards, it would be all 52 of the different cards. If you're flipping a coin, it would be heads or tails. Right? It's a list of every possible outcome. And that's pretty much the number of things in the sample space is always going to be the denominator of the probability question. When they're asking, what's the probability of something, something, something? Remember, it's favorable over total. And the sample space, since it includes everything, is going to be equal to the total number of things that can happen. So, of course, this is how we get our probability formula. The probability of any event E is the number of outcomes in E over the total number of outcomes in the sample space, as I mentioned. So it's favorable over total. That's what you want to remember with probability. And then we looked at a bunch of questions, of course. Remember, if there's any, I didn't include any deck of cards questions on the test because I don't want people to get confused about those, and I couldn't get it to include the deck of cards that I wanted it to. But of course, they are still a good example. Here we did an example with deck of cards. And then say the probability of getting a red 8, since there's 2 red 8s, the 8 of heart, the 8 of diamonds, right? There's 2 events favorable to getting a red 8 over the total, which would be 52, and that would give us our probability. So empirical probability, what we were just talking about here was theoretical probability because you can, in theory, figure out what your probability would be. But empirical probability, that's an observed probability. That's what empirical means. It means like an observed experiment. So in empirical probability questions, they're usually just measuring, right? They're measuring a certain number of things and putting them in a certain bucket. And then you can calculate the probabilities based on those, where it would just be, again, favorable over total. And we looked at examples of that as well. And then we came to, very importantly, the addition rule for probability. And remember, the addition rule for probability says that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B at the same time. Now, if the events are what's called mutually exclusive, which means there's no overlapping events between them, then this term right here ends up just being 0. But you can still always apply this formula. Just don't be scared that if this last term ends up being 0 because there's no overlap, that's fine. That happens all the time. Okay, and so we spoke about the addition rule of probability. So whenever you see the phrase or, you can do it this way. And we did a couple examples like that. Remember, probability has to be a fraction. That's why all these are little mini fractions right here, because they're all little mini probabilities. Looks like here there was basically an empirical probability question. But again, we see that key phrase of or to let us know that we've got to use the addition property. Okay, so of course, super important rule. And again, you want to use this when you see the phrase or. We've also got a multiplication rule. And we use this rule when we've got a question involving the and, probability of A and B. Okay? And so if the two events are independent, which means that they don't affect each other, they're completely different from each other. When you do event A, it doesn't influence event B at all. That's what it means for them to be independent. And if they are independent, it's just the probability of A times the probability of B. That would be the probability that both A and B occur. So the probability of A and B, this is equal to P of A times P of B, given A and B are independent. When they're dependent on each other, or when one depends on the other, we use what's called the conditional probability formula. But if they're independent, then our formula would be this right here. So we looked at a problem there. Right, they were two completely different events here. We were looking for the probability of rolling a 3 on a die and getting tails when flipping a coin. So it doesn't matter what you get on the die, right? It doesn't affect your coin flip at all. Similarly, the coin flip doesn't affect what you roll on the die at all. And so therefore, since they're independent, we could just do the probability of A, which I guess in this case would be the probability of rolling a 3 on a die, and B would be the probability of getting tails when flipping a coin. And then we just multiply them together to get the probability that both happen. And we want to use the conditional probability formula whenever they are dependent on each other. Okay, so there's two multiplication rules essentially. And the probability of A and B is equal to the probability of A times the probability of B given A if A and B are dependent. Remember, the way to read this notation right here means probability of B given A has happened. And so if A and B depend on each other, they influence each other somehow, it's going to change our probability calculation. Often it's going to change both the numerator and the denominator. Sometimes it'll just change the denominator. But you need to take into account what happened in event A when you're thinking about the probability of event B. So definitely a formula you need to remember and be aware of how to use. We looked at a good example here involving a deck of cards. 3 cards are drawn from a deck and not replaced. So not replaced means if we draw, say, the 9 of clubs, we don't put it back in the deck, and so therefore we can't get another 9 of clubs. And rather than having 52 cards to choose from, we would have 51. So it might change some things in our calculations. So, for example, when we're asking here what's the probability of getting 3 jacks, it's like jack and jack and jack. Well, since we're not replacing, these events depend on each other. So if we get 1 jack, then on our next pull, there's not going to be 4 jacks, there will actually be 3. There's not going to be 52 cards, there will actually be 51. And so the probability of getting 3 jacks in this, for example, right, the probability of getting the first jack would be 4 out of 52, because there's 4 jacks out of 52 total cards, favorable over total. Then we times it by the probability that the second card is a jack, given that the first card is a jack. So if we know that the first card was a jack, there's now only 3 jacks left for the numerator of our next calculation. So it's 4 over 52 times 3 over 51, right? There were 3 jacks to choose from and now 51 cards to choose from rather than 52. And on our third attempt of getting another jack, we're assuming that the first 2 cards were also jacks. So on our third pull, there's only 2 jacks to choose from and 50 cards to choose from, giving us that it would be this calculation. And I'm trying to write some of the notation there to help it make a little bit more sense. And then again, you just multiply them together. That's what the multiplication rule says. And it implies multiplication or implies addition. And same thing for the other ones as well. We want to get an ace, a king, and then a queen. So that would be 4 out of 52 times 4 out of 51 times 4 out of 50, right? Because once we pull the ace, there's still 4 kings left, so we don't change the numerator, but there's 51 cards, so we do change the denominator. Remember, it would look like this. And remember, there's this complement principle as well. And you want to use this whenever it says the phrase at least one. And the formula of the probability of at least 1 is equal to 1 minus the probability of none. It's the complement principle. In general, the formula would be the probability of at least x would be 1 minus the probability of not x. Remember, it's like the complement symbol. The line over it means complement. So the probability of at least 2 would be equal to the probability of 0 plus the probability of 1, essentially. Right? That gives every outcome. Wait, sorry. I meant to say, sorry, I messed that up. What am I doing here? Well, so what I want to say is there's a couple different ways you could do it. You could do the probability of 1 minus, so the opposite of at least 2 is 1 or less. And how would you get 1 or less? That would mean essentially 1 or 0, right? The opposite of at least 2 means 2 or more. The opposite of at least 2 would be less than 2, which would be either 0 or 1. So, yeah, that's all it would be right here. Probability of at least 3, for example, would be 1 minus the probability of 2 or 1 or 0. You basically would have to add all 3 of those probabilities up and then subtract 1 from that. And that's essentially the complement principle. You want to use that when you see the phrase at least. Specifically, at least 1 would be equal to 1 minus the probability of none, right? Because the opposite of at least 1 is less than 1, which there's only one option of, none. And so if you ever need to, add up a certain number of probabilities when it says at least or at most or something like that, make sure that you're on the lookout there. And then we come to counting rules, which are pretty tough. Definitely very tough. But the way that I teach my students these counting rules are by a flowchart, which I think is really good. And this is basically when you're counting a certain number of events. In how many ways can blah, blah, blah. In how many ways can blah, blah, blah. Sometimes these end up being crucial for a probability calculation. Maybe the way we have to put, when doing favorable over total, the number of ways to calculate the favorable events, we've got to use one of the counting rules. The number of ways for the total number of events, we've got to use one of the counting rules. So they do also end up getting paired up with probability questions. And this is what I tell my students. You got to ask yourself a couple questions. The first question you want to ask yourself is, are repetitions allowed? And if yes, if repetitions are allowed, we go to what's called the fundamental counting principle. And remember the fundamental counting principle, that's when you just write out the number of dashes representing the number of tasks in a problem. Then you put the number of ways that you could accomplish each task in each slot, and then you multiply them together. So that would be like, example. Let me just do a quick example. How many 4-digit numbers are there? Well, when we're counting the number of possible 4-digit numbers, there's 4 tasks, one for each digit. And then how many numbers can we put in each slot to make it a 4-digit number? Well, there's 9 that we can put here, namely 1 through 9, right? We can't put a 0 there because then it wouldn't be a 4-digit number. It would be at most a 3-digit number. And then in the next 3 slots, we can put anything between 0 and 9, so that would be 10 for each. Right? Repetitions are allowed. We can use the same numbers over and over again. And so we would get, 9,000. Right? That would be a good example of when and how to use the fundamental counting principle. But if you ask yourself, are repetitions allowed, and you say no, then you've either got to do a combination or a permutation. And to figure out to do a combination or permutation, you ask yourself a second question, which is, does order matter? And if you realize that order does matter, you want to use a permutation. I'll just say NPR. And if order doesn't matter, you want to use a combination. I guess I'll give the formulas for these. So NPR is, this is the smaller one. So this one is n factorial over, wait, let me just, before I say the wrong thing. No, permutation's the bigger one, rather, sorry. It's n factorial over n minus r factorial. And NCR is n factorial over r factorial times n minus r factorial. But if you have a scientific calculator, or perhaps on the calculator on the test, I think it also does have it on the calculator on the test. They've got formulas, or they've got algorithms for NCR and NPR already in there. You just got to plug in N and R. Remember, N is always the bigger number, and R is always the smaller number, the number of things that of group size that they're choosing. N is, let me just write it down. N is the total number of entries, I guess I'll call them. I don't know. And R is the group size that you're trying to see how many you could make of. I've made it very apparent in the questions on the test whether order matters or not, because I know that can be very ambiguous sometimes, especially in some of the homework questions and things like that. So there are some very key words. If you see the word arrangement or order, that means order matters. If you don't see that, then it basically means order doesn't matter. Okay, and that's basically what we talked about here, right? A couple of, here is a fundamental counting principle question. And then here's permutations, combinations, and here's the same flow chart that I've just mentioned here. Really, really important. And then the 4.5 questions are really, really tough. The mix of rules, I didn't include any of those on the test because they're just, they're really good questions to learn about. But as far as the test goes, they could be really, really tough. And I didn't include any on the test. Okay, so that's chapter 4, everything that I want you guys to be aware of and know, and all the formulas that you got to know, everything. Next, let's go to chapter 5. It is on probability distributions. So a probability distribution looks like this. We've got some variable x, and then the probability that that variable occurs. You know, maybe this will be, I'll call it little x1, little x2. There could be up to little xn of them. And then here, this is like the probability of the first one, the probability of the second, and the probability of the nth. And one important thing that lets you know if it's an actual probability distribution is that all the p's have to add up to 1. Right? All of these probabilities need to add up to 1, aka 100%. If you don't have the probability distribution adding up to 1, aka 100%, then you haven't listed all of the possible outcomes. Similarly, you can't have more than a probability of 1 because then you're saying something can happen more than 100% of the time, and that also doesn't make sense for the same, for similar reasons. So very importantly, the bottom column does need to add up to be 1. And so let's go ahead and look at here what we discussed and what we really need to know here. We did a couple examples of probability distributions. And again, here the sum of probabilities must add up to be 1. Section 5.1 is just talking about the anatomy, essentially, of a probability distribution. The meat and potatoes start in section 5.2, really. And so in section 5.2, we define some of the important measures that we often use. We've used them for other distributions. Here we're using them for a probability distribution. So, with different distribution, the same variables come along for the ride so that you can do the same kinds of comparisons, et cetera, et cetera. And we learned a couple of important formulas. One being the mean, aka mu, right? It's called mu. And the mean is just the sum of all the x's, right, the data value times their probability. So you multiply the first value times its probability, you add it to the second value times its probability, et cetera, et cetera, et cetera, until you get them all. And that would be the mu. And we've done a couple examples there, of course. And then we also definitely a formula that you've got to know how to use. We've also got the variance, of course, and the standard div. Remember, the variance is sigma squared, and the standard deviation, which is just regular old sigma. And the formulas for these are somewhat, it looks similar to the mean, right, the summation part, but it's instead of it being x, it's x squared. And then we subtract mu squared. We've got to also know what mu is, so that's why we calculate mean first, because we got to know it anyway in our variance and standard diff formulas. So the variance is the sum of all the x squareds times their probability minus mu squared. And the standard deviation is the square root of this. So, definitely not the easiest formulas to remember or to use, but of course we've got plenty of examples in the homeworks. We've got good examples here, plenty of YouTube examples as well on calculating this kind of stuff. So a lot of really good resources out there for practice. So definitely get a lot of good practice on these formulas here for probability distributions. Variance and standard div, of course, very, very important, no matter what the distribution is. So we did examples there as well. And then we also spoke about expected value, which is essentially what's going to happen on average. But it's not like a new formula or anything. And they call this E of X. Or just E. Sometimes EV, actually, as well, for expected value. And the expected value, I should not use that E. The expected value is just the mean. It's just mu. We expect, on average, the average to happen. That's essentially what we're saying. What do we expect to happen? Well, we expect the thing that happens on average to happen. Yeah, that's pretty much what this is saying. And we looked at some examples there. Um, Very often they're used in profit calculations. So there will be different outcomes, and then you'll either win or lose money depending on those outcomes, and then there will be a certain probability that you win or lose based on those outcomes. And your expected value is just the mean. So on average, if you find that your expected value is negative, like it was in this example, well, we definitely shouldn't play that because we're going to lose money. On average, we're going to lose a quarter every time we play. And if we play it, 1,000 times, it's going to end up being a lot of money at some point. This is how casinos make money off blackjack and things like that. It might not look like a lot of money with one bet, but if you got somebody at a blackjack table doing 1,000 bets, they're almost certainly will just lose all their money at this rate, right? And so that's why expected value calculations can be really, really important. And we also talk about the binomial distribution in Chapter 5. And remember, the binomial distribution, what does binomial mean? It means there's two options, success or failure, yes or no, good or bad, on or off. And very often this is used in like survey questions because they'll ask somebody a yes or no question. A certain number of people will say yes or no, and then that will be the success or failure in the formula. Right? And so that's what we talked about here. It's not a nice formula. I gave a little bit alternative version of this that's better later on in that review video. And remember, it's P of X. Let me actually give a preamble for it. The probability of exactly X successes in N attempts is, so it's P of X is equal to NCX times, what is it, P to the, I can never remember, P to the X times Q to the N minus X. This is the formula that I instruct you guys to use. And yeah, it's definitely not a nice one. Again, remember, P is the probability of a success, of a single success. And therefore, Q is just 1 minus P. Because you could either succeed or fail, so it's got to be the complement, essentially. Okay, and so we did a couple examples there. Very often it's like a word problem, and they're going to tell you what the P is. They'll tell you what the N is. And they'll tell you exactly how many they want to see what the probability is of. So, go through the problem, identify what the specific values are, and then you got to plug them into the formula. So definitely be really careful. Of course, this calculation can be very, very difficult. A lot of room for error, a lot of room to make mistakes in just doing the calculation. So double, triple check your work when doing this. Of course, if you get a number above 1, it's wrong. If you get a number below 0, it's wrong. It's got to be between 0 and 1. So if you get some like 500 number, you've done something wrong, maybe try again. And that's our formula right there. We did a couple examples as well. And we also discussed what mu, sigma squared, and sigma are for binomial distribution. And remember, mu is just NP, sigma squared is NPQ, and sigma is square root NPQ. Okay. And chapter 6, remember, is on the normal distribution. Okay, so what did we say about the normal distribution? Remember, the normal distribution are distributions which have this bell-shaped curve shape, symmetric and bell-shaped, right? These are the properties of the normal distribution. It's bell-shaped and symmetric about the mean. The mean, median, and mode are equal and lie at the center. The total area under the curve is 100%, which represents probability. And we've got what's called the empirical rule, which tells us what percentage of the data lies a certain number of standard deviations within that space away from the mean. So the empirical rule says that, if we go one standard deviation away from the mean in each direction, that will encompass 68% of the data. If we go 2 standard deviations away from the mean in each direction, that will encompass 95% of the data. If we go 3 in each direction, that will be 99.7% of the data. Definitely, you want to remember those numbers, 68, 95, 99.7. Also, if we want, the z-score of a data value relates how many standard deviations that data value is away from the mean. So a positive z-score means you're to the right of the mean. A negative z-score means you're to the left of the mean. And if you've got a z-score of 1, that means you're exactly 1 standard deviation to the right of the mean, etc., etc. So the z-score tells us on the normal distribution how many z-scores we are away from the mean. And we use what are called z-tables to find the area under a curve. Specifically, the z-tables give us the area to the left of a z-value. So if we ever want to find the area to the right of a z-value, we just do 1 minus the area to the left of the z-value. And so, these z-tables are going to be on the test. You just have to, there's a little table button that you got to click, and then these come up. So if you ever want to find the area to the left of a z-score, to the right of a z-score, or between z-scores, you've got to know how to use these charts. So we did a couple examples here, finding the area to the left of a z-score, to the right of a z-score, between z-scores. Remember the area between 2 z-scores? It's always the area of to the left of the bigger z-score minus the area to the left of the smaller z-score. So the one on the right minus the one on the left. And then, we talked about applications, which, remember, is really just talking about the z-score. It's just z-score questions, and then applying that to the probability under the curve. And remember, a z-score is just the data value minus the mean over the standard deviation. Okay, and so we have had examples like that as well. The only difference here is we just have to come up with the z, right? In 6.1, they're giving us the z's, asking us to find the area between certain z's, or to the left or to the right of certain z's. 6.2, we have to come up with the z ourselves and then calculate the area accordingly. If we're finding the percentage of people who have less than something, we want to find the area to the left of that z-score. If we want to find the percentage of people who have more than something, we find the area to the right of that z-score. Between something, we find the area between the z-scores, right? So we saw examples like those as well. And also, the question could go the other way around. So this is another good formula to have, which is that if we have a value or an area represented by some representing some probability, and we want to see what z-score was representative of that value, then we use this formula. X is equal to z sigma plus mu. Which you can, of course, just get from solving the above formula for x. And so if there's ever a certain percentage and you need to find the z value for that, you got to read the charts backwards. You find the area you're looking for. So for example, in this question, we were looking for what's the z-score that separates this value, separates the top 10%. So to find the z value, I know that the area to the left of it is actually 90%. And then I look for the z value that gives us the area to the left of it being 90% or 0.90. So I just search for the thing closest to 0.90. Not every value is going to be represented here. You have to find the closest value to it, and then that will give you the z-score accordingly. Then using that z-score with the given mu and the given sigma, you can come up with the value representing that percentage. We then came to the central limit theorem, which we use when there's more than just one sample. It's more than just n being 1, essentially. So if there's a certain number of people in the survey or a certain number of, something being tested, then we've got to use, it's a very similar z-score formula, but instead the denominator, it's sigma divided by square root of n. And so when you could pretty much always use this formula, you could use it if n is 1, you just get the first formula right here. So you would just have to know that n is 1 when it doesn't say what n is, essentially, I guess. And then the questions are the same, using that z-score that you get here, find the area to the right of it, to the left of it, between certain values, etc., etc. So when the sample is of more than just one entry, like here in this example, there was a sample of 36 people. So if you can identify what your n is, and you're looking for some z-score to come up with this probability, you know that you've got to use this formula, the one with the n in it, right? Okay, and then we come to section 6.4. And this one's on the normal approximation of the binomial distribution. And we've got a couple things from this. We've got mu is n times p, and the standard div is square npq. The variance is npq. And we've got to, since it's an approximation of the binomial distribution, we've got to use what are these? These are called the corrections for continuity. So for ever equal to a value, we're finding the probability equal to a value. We've got to set it up. We subtract a half of a unit from x and add a half unit to x, and find the value between those values. So really, you just really have to memorize this chart. I'll put this chart here in this review. So that, the correction for continuity, I know it's a bit annoying, but I don't think they give this chart, so definitely you want to memorize this going into there as well. And we looked at an example or two like that, just one actually. So again, it's a binomial question because they're just asking the people, have you fallen asleep at the wheel, yes or no? So when you could boil the answers down into just two different possible answers, it's a binomial distribution question. That's what lets us know we've got to use these formulas instead. And in this case, our n would be 200. we're looking for the probability that 62 say that we'll have fallen asleep at the wheel. So in this case, we would be using the first criteria for the correction for continuity, because we're looking for the probability that exactly 62 will say that they have fallen asleep. So instead, what we would be looking for is probably between 61.5 and 62.5, which is what I've shown right here. So we calculate two different z-values, one for 61.5, one for 62.5, and then we can calculate the area between that. So just be aware of the other corrections for continuity. If you're looking for the probability greater than or equal to some value, you switch it to strictly greater than, and you subtract a half a unit from the value. If it's strictly greater than some value, you add a half unit and make it strictly greater than. Essentially, what they're trying to do is get rid of the equal sign underneath. Right? Everything on the right, there's no equal sign. Everything on the left, there's either an equal sign or not. And so for these ones, it's just pushing it a little bit further so that it's a little bit away from the value that we're actually looking at. So just be aware of these corrections for continuity. Definitely make sure you know what they are going into the test. And that would be it. It's a 10-question test. There's 3 questions on Chapter 4. 2 questions on... No, that's not right. 1, 2, 3, 1, 2... Yeah, actually it is right. 2 questions on Chapter 5. 5 questions on Chapter 6. And again, you've got plenty of time to study still, right? The test will be open, you've got the whole 2 weeks from its open date to the due date, and then if you complete it a week after that, you still got a week after that for it to be late. But I would, the test is an extremely large portion of your grade. Definitely don't get it in late. Get that in on time, please, 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 to avoid that late grade. Email me if you have any specific questions while studying. The way that I encourage you guys to study is watch the review videos of each chapter that I've posted, especially if there's a chapter that you're having a lot of difficulty on. Maybe watch that review video a couple times. Maybe do the homework questions over and over and over again. Do the try to redo the quiz. Maybe change some of the values around. Try it again. Double check your solutions, etc., etc. Maybe you can find somebody in class to study with if possible. And as always, again, feel free to email me questions. If you're available to come to my in-person office hours, do that. You can do that as well. If you can't, try to email me specific questions, and I'll always get back to you within like a day or two with very detailed response. And let's see, is there anything else? I think that's it. If there's anything else that I need to mention, I guess I'll probably send out an email or so. And so good luck on the test, everybody. Make sure, don't just take it on the first day that's available. You've got 2 weeks to take it. Make sure that you use that full 2 weeks to your advantage to study from. Let me know if you need help, if you need extra practice, anything like that. And I wish you all the best of luck on the test. So good luck on the test, everybody. We'll then, after the 2 weeks are over, I'll then be posting the new material, and I'll be sending out emails around that time and everything. And so good luck on the test, and I'll see you guys all in the next video. Have a great day.